for your observation. We have like small telescope.
Oh, no, we actually use our phone.
Okay, everyone, let's start. So for today, we're really happy to have Shreya Vardhan from Stanford University. It's kind of a homecoming game because Shreya did her bachelor's and her PhD here in Cambridge, although, yeah, both here and I guess down the street at MIT for PhD. So it's really great to have her here, and she'll tell us about estimating time in quantum chaotic systems.
Okay, great. Yeah, thanks a lot for the invitation. It's wonderful to be back here. So today I'm going to be talking about some work in progress with Haifeng Tang, who is a graduate student at Stanford, and Jinzhao Wang, who is a postdoc there. The subject of my talk is estimating time in quantum chaotic systems and black holes, and I'll explain what this means. So I'm going to first.
Maybe let's get rid of the message. Thanks.
Okay. So.
Yeah, great, thank you.
I'm going to start with some background and motivations. And first I'm going to start with some motivation from just general chaotic quantum many-body systems. And I'll explain shortly what this has to do with black holes. So suppose that we have some chaotic many-body system and we expect that any initial state, even if it's very highly out of equilibrium, will reach some kind of equilibrium state at late times. So if I start with the setup where I have a gas where all of its molecules are in some very specialized configuration, like I put them in the left half of the box, then eventually I expect that they'll spread out and then at late times things will reach some kind of steady state. So in particular, I'm interested in the setup of quantum many-body systems where I can imagine that I have some pure state psi 0 initially, which evolves under the chaotic many-body Hamiltonian age. Then under this evolution, if I consider some simple observable, like the density of particles on the left half of the box in this picture, then I expect that it roughly shows some behavior like on the left plot here, where it somewhat smoothly decays and then reaches some final almost constant equilibrium values. There will be some small fluctuations on top of this, but essentially the picture looks like this. Okay. And in contrast, if I have some very specialized configuration, like if I have no interactions between the particles for some reason, or some very fine-tuned interactions such that the system is integrable, then I might expect a picture like the one on the right, where maybe initially the density on the left half will decay, but then it might show some very irregular behavior where it might go back up and keep oscillating and so on. Okay, but that is supposed to be a very non-generic situation. Universally, in most systems, I expect the situation on the left. And then if I'm in this situation at the end in this regime, at the end of this picture, then essentially, it seems like I can do very little to distinguish between different times within this regime. Okay, so it seems like it's going to somehow become increasingly hard to tell the difference between different times at late times in a chaotic system. This might not be the case so much in an integrable system. And my goal in this talk will be to make such statements more precise and test to what extent they're true. So can we precisely quantify our ability to estimate the time t from time evolved state psi of t? And if so, then based on this intuition, does it become negligible at late times in chaotic systems? And is this ability to estimate time somehow better in integrable systems? So the reason that this is related to black holes is that I can think of black holes as examples of exactly the same kinds of systems that I described on the previous slide. So I could imagine that I have some star in initial pure state psi 0, which collapses to form a black hole. And subsequently, we know that the black hole emits some thermal radiation. And there is a lot of evidence from like things that were done over the last 40 years that black holes can essentially be seen as examples of highly chaotic quantum many-body systems. So in particular, in this process where a star collapses to form a black hole, this step where it's collapsing and forming a black hole can be seen as something like the approach to equilibrium on my previous slide. So the region where things were decaying. And then at late times, as the black hole is emitting radiation, I can think of the combined state of the black hole and the radiation at any point in this process as some kind of macroscopically equilibrated state. And then the change in the state is coming from the fact that degrees of freedom are being gradually transferred from the black hole to the radiation. But that is happening on some slow time scale. And at each point in this process, I can think of the state as being in some kind of equilibrium. Okay, so this is like the part of my curve on the previous slide where things had saturated the chaotic system. So then again, in this process, it's natural to ask if throughout this process of equilibration, our ability to estimate time locally is getting increasingly worse at later times in this process. And also, in this context, it's very natural to ask if I have access to only some subsystem, like the radiation of the black hole, then can I do a good job still of estimating time or not?
Shreya, are you
Yes.
giving yourself access to arbitrary operators or just the state?
Good question. I'm giving myself access to, so far, in principle, arbitrary measurements on the state. And maybe I have multiple copies of the state, so I'll explain the setup more precisely very soon. Okay, so we might expect that in this situation I described, there might be some kind of tension between thermalization and some constraint from unitarity in the system. Because at late enough times, my intuition that things have become constant in the state is coming from the fact that it resembles some thermal density matrix, like e to the minus beta h. And for e to the minus beta h, it's exactly true that it doesn't evolve at all with time. It just commutes with the Hamiltonian. And so there's just nothing I can do to estimate time in that state. But unlike e to the minus beta h, the actual time evolved state that we get from some unitary evolution has some decomposition like this in terms of the eigenstates of the system. And there is essentially no way that this can exactly stop evolving unless it already started out as an eigenstate of the system. So this suggests that there may be some tension between thermalization, what we expect from thermalization and actual constraints from unitarity. And in the context of the black hole information problem, there is another distinction between e to the minus beta h and this time evolved state, which plays a really important role, which is that the former state in some sense contains no information, while the latter still contains information, but in a very scrambled form. Okay, and in the black hole information problem, we discussed how unitarity puts some constraint on the entanglement entropy of subsystems in the time evolved state, and those constraints are violated by the thermal state. Okay. So in this talk, one of the questions we try to ask is whether unitarity also puts constraints on our ability to estimate time. Okay, so we'll use general properties of chaotic quantum many-body systems in this talk to make predictions about this question of estimating time in black holes. And just to put everyone on the same page about this general approach, I'm going to review how this kind of approach is used in the context of the black hole information problem, where, as I mentioned, we consider entanglement entropies of the black hole and the radiation during the evaporation process. And from unitarity, we have the general constraint that the entanglement entropy of the black hole has to be equal to the entanglement entropy of the radiation throughout this process. If I started with an initial state, which is a pure state. In contrast, so the prediction from Hawking's calculation in semi-classical gravity was that the entanglement entropy of the black hole follows this curve, the blue curve, and then the entanglement entropy of the radiation follows this red curve. Okay. So in particular, at late times, the entanglement entropy of the radiation is much bigger than that of the black hole, which seems to very badly violate the constraint from unitarity. Yeah, we expect that somehow unitarity should not be violated in any fundamental theory. And so if we make the assumption that the dynamics of the black hole are both chaotic and unitary, then it's natural to make a model for the late time state of the black hole and the radiation as some kind of random pure state. Okay, so this means that I model the whole system as some finite dimensional Hilbert space and consider pure states randomly with the uniform measure in this Hilbert space. And I divide the system into two parts, A and A bar. And you can do this calculation explicitly. And by doing this, Page found that the entanglement entropy of any subsystem A is given by the minimum of the log of the dimension of A and the log of the dimension of A bar. Okay, so in particular, in the context of black hole evaporation, if we take A to be either the black hole or the radiation, then this formula predicts that the entanglement entropies of both will follow this Page curve, which is the minimum of these two.
Can I ask a question?
Yes.
You said that the entropy of the radiation and the black hole have to be the same, plus it's unitary.
Yeah.
But doesn't the entropy have to shift as the black hole evaporates? Is that true for all time?
So the number of degrees of freedom is shifting. But if you look at the entanglement entropy as defined in terms of the quantum state and the reduced density matrix, there is a constraint from unitarity that can be smaller than the actual number of degrees of freedom in the system. And the prediction is that that microscopic quantity has to follow this minimum curve. What you're saying is true of the number of degrees of freedom in the black hole, which is continuously decreasing, and the number of degrees of freedom in the radiation, which is continuously increasing.
I see.
If the radiation is submaximally entangled with the with the black hole.
I see. I got it.
Any other questions? Okay. So this was a prediction that was made for black holes just based on general properties of highly chaotic systems. In recent work, it was also confirmed by using new ingredients that modified Hawking's original semi-classical gravity calculation. And these involved adding things called islands and replica wormholes into the calculation. And then we were able to exactly reproduce this page code. Okay. Through this process, we also learned more about quantum gravity by making some prediction about how the system should behave based on general properties of chaotic systems. So what we'll try to do in this talk is make a similar kind of prediction for what happens based on general chaotic systems for this task of estimating time. Okay. Good. So let me explain more precisely what I mean by this time estimation task. So in the general many-body system context, we're given some number of copies, which could be large, of the time-evolved quantum many-body state of the system at some time t plus delta t. Okay, so this means that we know, so what we know is we know what the initial state psi zero of the system is, and we know what Hamiltonian it was evolved by, and we know that the time is somewhere in the neighborhood of some time t. Okay? But we don't know the precise value of t plus delta t, we're just given the state at that particular time. And somehow we want to make measurements on the state that's given to us in order to deduce what delta t is. Okay, so this is some task of local estimation of parameter time in the time-evolved state. Okay, so we can consider the state on the whole system, and we can also consider the case where we're restricted to making measurements on some subsystem of the whole system. In which case, the relevant thing to consider is the time evolution of the reduced density matrix of that subsystem. Okay. And in particular, in the setup of the black hole and its radiation, we're considering this late time state of the black hole and radiation. And again, we know so we have some rough estimate for the timers, and in particular, that tells us, that fixes the relative sizes of the black hole and the radiation. So we assume that that process of degrees of freedom being transferred from the black hole to the radiation is happening on some slow time scale. But then we want to consider the evolution of the state on smaller time scales. And locally, we want to estimate what delta t is if we're given the state of the radiation at some particular time. Okay, and again, we have some information like what the initial state of the star was and what the Hamiltonian is of the whole system. Okay, so our question is whether we can estimate delta t in this case by making measurements on ρr. And we'll try to address this question by answering the previous question. Okay. Any questions?
Yeah,
Yeah.
just within Hawking radiation approach,
Mhm.
if I know the state at some time t,
Yeah.
at t plus delta t, the amount of radiation in the exterior is going to be larger because of the Hawking radiation that was emitted.
Mhm.
So given that formula, if I just measure the energy, I know how much time has elapsed.
Yeah.
But you're asking something deeper than that, right? This
I'm
is
asking something different from that.
different from that, okay.
Yeah, because I'm assuming that the scale on which degrees of freedom are time scale on which degrees of freedom are transferred from B to R, I'm assuming is much slower. So I'm considering a case where the sizes of B and R are fixed. Okay, but then even on that, but then the state is still evolving between the times when
Okay,
black hole and radiation are of a certain size and when they're of a certain other size, and I want to ask about that evolution.
okay.
Other questions? Okay, so so in order to set up sort of how I'm going to ask this question or what quantities I'm going to use, I have to introduce a few things from the general theory of parameter estimation in quantum metrology. So that's what the next few slides are going to be about. So now I'm going to consider, even for the next few slides, we can have a more general discussion where we consider some one parameter family of states, rho of x, labeled by some continuous parameter x. And in our case, eventually we want to take x to be the time. But say for now, the discussion could even be completely different. And so we are experimentalists and we're given n copies of rho x0 for some particular value x0 of x. And we want to figure out what x0 is by making measurements on this state. So, very explicitly, suppose we have some spin 1/2 system and we choose to measure the Pauli Z operator on all sides of my switching. So then the first time I do this measurement, I get some string of outcomes, of zeros and ones. And then I can repeat this n times and I get some other string each time. Okay. So I have these n outcomes, and based on these, I want to come up with some estimator function. So I want to plug these n outputs into some estimator function, which gives me a guess for the value of x0 based on my measurement. Okay. And our question is, how well can the best possible function do at estimating the actual value of x0? So in particular, if no estimator was able to do a good job, then this would indicate that rho of x is just not changing much with respect to the parameter x, at least with respect to these measurements. Yeah.
Do these estimators act jointly on all the copies of the states, or do they act in parallel?
It turns out that you actually don't get an advantage by considering measurements jointly on many copies for this particular.
So here, I'm confused a little bit because this estimator function, what if it's just literally exactly the function that tells you what x naught is? I mean, you haven't rolled that out as a possible estimator function.
I guess
here.
I don't, the input of this function is these n measurement outcomes.
Right.
So I don't know how to come up with, I need some function of just these things.
I understand. I think my confusion is that you haven't said, and you haven't given any restrictions on how you're coming up with the estimate, and you haven't excluded the possibility that you just luckily happen to come up with something that exactly lands you on the right answer every time. So what I'd like to understand is, how would you know, or under what are the conditions? I feel like you have some conditions on the estimator you're just not stating here.
So I'm assuming that my only knowledge is of the initial state and age. And I don't know the exact value of t or t plus delta t, like I haven't really said.
Maybe what will help me is if you tell me what capital N is.
Capital N is anything.
Okay, so if N is exponential in the size of the Hilbert space, then I think you can pretty much always get
yeah,
a
you can
good
do
estimate.
tomography and but I want to consider N, which is large but not large but auto one with respect to the size of the.
I see. Okay.
Yeah, so it's not like I can just figure out exactly what the state is and then.
Right. I mean, because so far it looks like you can, but.
Yeah, good. So I'm assuming some auto one number of measurements. And yeah, it'll turn out that there is some fundamental bound on how much I can do this, which will be expressed just in terms of properties of the state. So I can't do an arbitrarily good job. Okay, great. Any other questions? Okay, so this estimation task is giving me some sense of how much rho of x is changing with x, at least in this measurement basis. And in order to quantify how good the estimator is, it's natural to consider some object like this, where I look at the difference in the value between what the estimator gives me and the actual value x0. And then I can average this over all possible outcomes from the probability distribution of the state at the actual value x0. So these probabilities are just given by the usual rule in quantum mechanics. Okay. So I want to quantify the size of this object. And if this is large, then it's telling me that the estimator is not doing a good job. And now this is actually phrased in this way at the level of this equation, just a task about inferring some parameter x0 in some classical probability distribution by using some number of samples from that distribution. Okay, so this is something that is very practical and has been used a lot in actual statistical inference, and was studied a long time ago because it's not even a question about quantum mechanics. Okay, yeah, so it turns out that this object has a known lower bound over all possible choices of the estimator function. And this can be expressed just in terms of intrinsic properties of the probability distribution. Okay, so for any choice of the estimator function, this quantity by 1 over n, where n is the number of samples that I draw, times something called the Fisher information, which is this particular thing expressed in terms of all possible outcomes psi of the probability distribution, and the actual value of the distribution at psi, and derivatives of the distribution with respect to the parameter x. Okay, so it's natural that this derivative should show up here because I want to see like this, the ability to do this will only be good if the derivative is large. And in particular, so all right, so this is telling me that as I increase the number of samples, my ability to do this task is improving because the variance is getting smaller. but say the Fisher information was just 0, then even if I took an arbitrary number of samples, I would not be able to do anything to estimate the parameter. So the value of the Fisher information is saying so how quickly I converge to the optimal thing. Okay, and it turns out that not only is this an inequality, it can also be saturated for some explicitly known estimator function for large enough n. Okay, and this is something called the maximum likelihood estimate, which again is very practical and is used a lot in statistics. Okay, so yeah, so this should be seen as a measure of how good a job I can do at estimating parameters. But now we actually have some quantum states, so we don't just have to consider a particular choice of the measurement basis. We can optimize the value of the Fisher information over all possible choices of the basis that we can measure in. Okay, and this gives us a quantity called the quantum Fisher information. Now this has become a question about local estimation of the parameter because the optimal measurement basis depends on the state itself. So you need to have some idea of what the value of x is, and then you can improve your estimate by making further measurements. Okay, and yeah, so this is just to show you that this quantity has some explicit formula which involves the eigenvalues and eigenstates of the density matrix X and its derivative with respect to the parameter the density matrix rho of X and its derivative with respect to the parameter X. Okay. Yeah. So another way of writing this quantum Fisher information, which is useful, is to notice that it can be written as some kind of distance measure between the state at x and the state at x plus dx. So there are many different measures you can use. It turns out the one that's relevant for the quantum Fisher information is the so-called Beer's distance, which is related to fidelity, which some of you may be familiar with. But in any case, this is like some kind of derivative, how quickly the state is changing with the parameter x. And in our case, where we'll take x to be t, this can be viewed as some kind of intrinsic velocity associated with changes in the state. Okay. Okay, so this is the quantity that we'll be using for most of the talk. So the plan will be to use to first introduce some general properties of this quantum Fisher information, and in particular, to understand that it does have certain constraints from unitarity, like we anticipated earlier. And then we'll discuss the results for how this quantity behaves in chaotic as well as integrable spin chain models, and also in random pure states. So those will then give us some predictions for the case of evaporating black holes. And I'll discuss those consequences. And then I'll discuss the physical understanding of these results in terms of what they mean for the structure of the state. And finally, I'll also consider, instead of considering the optimal thing, which is the quantum Fisher information, the case of the classical Fisher information associated with simple measurements, and what implications that has in the black hole setup. Okay. So any more questions at this point? Yeah.
I guess I'm coming from like a Bayesian analysis point of view. Normally, when you do Fisher information, you have like a likelihood estimate. If I understand correctly,
Yeah.
you're saying the estimator is kind of like the analogy that the estimator is a likelihood function.
Yeah, you can define, right. So you can use in particular the maximum likelihood estimate.
Yeah.
And that is the thing which for large enough n converges to saturate the Figueroa bound.
Yeah, but is a goal to figure out what the likelihood function is, or are you just picking an equivalent of a likelihood function?
So if I assume that I'm choosing the optimal estimator.
Yeah, so you're assuming that there exists a likelihood that's optimal. Sorry.
What do you mean I'm assuming a likelihood that's optimal?
Sorry, I'm just trying to
I guess I'm assuming. So right. So there is some particular explicit choice of the estimator function.
Yeah.
For which this thing will be true as an equality. And I am so assuming that, then the relevant quantity to look at is the Fisher information or the quantum Fisher information if I optimize over measurements. So and first, just for most of the talk, I'll just discuss the behavior of this quantity. Maybe at the end, I can also if you're interested, talk a little bit about what this maximum likelihood estimation looks like. Yeah. Mm-hmm.
So you're looking at these poly matrices to project the spin measurements.
That was just an example. So that was an example of a particular choice of measurement basis. But actually, if I look at the quantum Fisher information, where I've optimized over all possible measurement bases, then that is not the relevant basis.
So this, I think, in statistics is a sufficient statistic or something to make sure that your measurement basis captures all the information in the system. There are ways of quantifying whether the basis you've picked is optimal.
Okay.
Is there an analogy here, or how do you select your measurement basis is the question?
Oh, so yeah, there is an explicit expression for the measurement basis such that the classical Fisher information in that basis is equal to the quantum Fisher information. That has some, yeah, like I think, right. So it's related to you do some super operator on this derivative of the state with respect to X and look at its eigenbasis. And then you measure in that basis. So it has some very explicit form,
okay.
But that is very different from this product basis that I was mentioning earlier.
Okay.
Yeah.
And what about the priors? What kinds of priors? Because when you make a likelihood kind of estimator,
Mhm.
you have the ability to put in priors, right? So do you have any priors there?
What exactly do you mean by priors? So I have the information that I said. So I have the state size 0, which is the initial state, and I know the Hamiltonian, and I have given some number of measurement outcomes.
I think priors is like equivalent to like the geometry of the domain of values that the measurements can take.
Or even a range?
Yeah.
I know what values the measurements can take because I'm choosing a particular basis to measure in. So in particular, in the Pauli case, I knew that the possible outcomes were either 0s or 1s at every side.
Maybe the choice of basis actually is the prior.
Yeah, if by prior you mean the possible measurement outcomes, then I know all of
Yes,
those.
yeah.
Mhm. And I also know sort of the analytic form of the probability distribution as a function of time. I just don't know what the actual value of time is. Okay. Great. So I'm going to use this quantity, and let's first discuss the general properties of this and the constraints from unitarity. So, right. So going back to sort of my first slide, from the fact that the state was relaxing to some steady state, what I originally expected was that this quantum Fisher information would monotonically decrease and go to 0 if I have a chaotic system, because it's thermalizing, it's approaching some steady state. And in fact, you can look at the behavior of so as I mentioned, the classical Fisher information is a quantity which can be defined for any probability distribution, including some classical probability distribution. And I can always consider some stochastic evolution of a classical probability distribution, which gives me relaxation dynamics. Like for instance, if I evolve it by the Fokker-Planck equation that describes diffusion. And in that case, this has been studied actually somewhat recently in the classical stat mech literature by these authors, and they found that indeed the classical Fisher information just decays monotonically in this process and goes to 0. Okay. But if you just plug into the formula that I had before and use that your state is given by this time evolution, and you're considering the full system, then it turns out that this quantity is just a constant with time. Okay, so it doesn't decay at all. So from this perspective, the state on the whole system is not relaxing at all. Okay, which is consistent with the rough intuition I had at the beginning that it looked like the state could not stop evolving if I was considering it. In particular, if I consider the case of a pure state, then this quantity is just proportional to the energy variance of the state, which we know is a constant for all times. And in particular, for an energy eigenstate, this is just equal to 0, which makes perfect sense because an eigenstate doesn't evolve, so there's nothing you can do to figure out the time in that state. Okay. But if instead I consider a typical product state and some local Hamiltonian, then the value of the variance is usually proportional to the volume of the system. And so the Fisher information is also proportional to the volume in that case. So it's quite large, and it's large for all times, so I can do a pretty good job of estimating the time in some optimum.
Shreya, can I think of
Yes.
this as essentially the statement that if you have a quantum system and it's evolving unitarily, a pure state is always going to be a pure state, no matter how close it looks to thermal naively?
I think it's not exactly that statement,
Uh-huh.
but I think it's very similar in spirit. So this was my last one. But
Oh, I see. Okay.
yeah, right. So it's like the statement that whatever it is always constant with time. But it's not like this. What the input that goes into showing this is different from the input that goes into showing this. Right. Yeah. But
Would the QFI of the thermal state also be exactly zero?
Yes. Because basically anything that is not evolving with time at all. The relevant object which goes into this is the commutator of the state with the Hamiltonian. So if it's e to the minus beta h, it commutes with the Hamiltonian, I always get zero. Good question. Great. So this is telling me that if I'm allowed optimal measurements, my ability to distinguish rho of t from t plus dt is just independent of t. Okay. So then, based on the comment that Netta made, we might expect that, what we need to do to see something more consistent with our intuition about thermalization is to consider the reduced density matrix on some subsystem. Okay, so now we want to consider the evolution of the quantum Fisher information of rho a of t for some subsystem A. And so again, this has some formula, which I just want to show you that it can be written down, and it involves the commutator of H, again with the global state, rho of t. Then you take some reduced density matrix of that. Okay, so this is rather different from the formula, the kind of formula that we have for the entanglement entropy, because it depends not only on the eigenvalues of the state, but also on its eigenvectors, which are these psi i's. And in fact, it also depends on the eigenvectors of the reduced density matrix of the complementary system. Okay, so it's a different quantity. And as was already mentioned, if you consider the case where rho of t is e to the minus beta h, then by putting into this formula, you find that the Fisher information of the subsystem is zero. But yeah, if our state is actually some non-trivial state, then yeah, this is a difficult thing to calculate, and we're going to have to do it numerically and by various approximations. Okay, so in particular, yeah, just to mention specifically one slightly technical point, that every state any quantum state can always be given some Schmidt decomposition between A and A bar, which involves Schmidt eigenvalues and eigenvectors. And we can give some explicit expression for the Fisher information in terms of the Hamiltonian, these Schmidt eigenvalues, and also the Schmidt vectors. And in particular, the Fisher information of A also involves the Schmidt vectors on A bar. Okay, so we're probing much more about the structure of the state using this one. Okay. So now let me mention the results that I get in chaotic and integrable spin chain models, and how they're consistent or not consistent with our intuition about thermalization. Okay. So I'll consider this chaotic spin chain model where I have something like an Ising model with both transverse and longitudinal fields. And the reason for using this model is just that it's been used to study a lot of different quantities related to quantum chaos, and it exhibits very generic behaviors that are seen in other chaotic systems. Okay, so in particular, if we had considered initial random product states in the system and looked at the evolution of the entanglement entropy of a subsystem, then we see a behavior which is very similar to what we see in holographic CFTs, where we see a simple linear growth followed by saturation, and the saturation value is exactly the page value. Okay, so in our case, we will consider the whole system on some number of size n, and we consider a subsystem of size NA. And sometimes I'll use dA and D to refer to the dimensions of the subsystem and the whole system. Okay, and we look at this quantum Fisher information associated with the subsystem. Yeah.
What is it that makes that chaotic?
I think it's
Any G and H, it will be chaotic, or
oh yeah, almost any G and H. So for generic values, it's chaotic. If you turn off the longitudinal coupling H, then it becomes the transverse Ising model, which is just a free fermion model. So that case is integrable. Yeah.
Okay.
So this is why we'll be able to study both the integrable and chaotic cases using this.
I see. Okay.
Okay. Great. So our first result is that if we consider a subsystem which is smaller than half of the system, then we see this kind of behavior. So in particular here, I'm fixing the size of the subsystem to just be 1, and considering different sizes from 8 to 12 of the full system. Okay, so I see that there is a monotonic decay, and then the saturation value is, so I'm plotting the log of the quantity. So the saturation value based on this plot is decaying exponentially with the size of the full system. Yeah.
Is this decay parallel or exponential?
The decay is not exponential, it's parallel.
And do
But like the decay with time,
you expect in a larger system for sort of parallel? Or?
probably, yeah. No, sorry, in a large N system, I would expect that it's exponential. But I don't know. Yeah, so good. So we're finding that this decays monotonically with time, and yeah, and the saturation value, if you study it in more detail for larger subsystems, then it turns out that it's proportional to dA squared over D. Okay, for a small subsystem, this is giving us a behavior which is exactly consistent with our intuition about thermalization, that the state is relaxing to a steady state and then eventually reaching something like a steady state. Okay. Good, and this is like, this curve looks so smooth because it was also obtained after averaging over different initial random product states. Okay. But now if we consider a subsystem which is bigger than half of the system, then we see a very different behavior. So now here I'm fixing the size of the full system and plotting the Fisher information subsystem, but now this is no longer on a log scale. Okay, so we see that in this case, this is just essentially the plot we already saw for less than half of the system. But for more than half of the system, there is a sort of dramatic increase in the values, which are now scaling with the size of the subsystem. And it's roughly like a volume law with the size of the subsystem. And also the time evolution is now not very non-trivial, and it's initially decaying and then actually shows an increase at intermediate times, which is very counterintuitive.
It's like an easy-like system, right? Is it, there's the intuition here, that, I don't know, it forms islands and they, like, what's happening is like it forms like some state and they fuse and then one state wins out over the other.
Yeah, it looks like there's right from this non-homogeneous behavior, it looks like there's a competition between two things.
Yeah.
I can explain a little bit later what those two things are.
Okay.
Yeah, and also as you're saying, it has a little bit of a similar flavor to islands in that there's sudden change after the halfway point, which
Yeah.
I'll also talk about.
Okay.
Yep.
So is there any intuition for the sudden decay? Like what's the physics between
For the decay,
for the decay? Yeah.
I guess the decay is very intuitive, just from the perspective that we expect that the state is relaxing, or at least on less than half the system is relaxing to some steady state at late times. So you would think that it's gradually getting closer and closer to that and doesn't fluctuate very much. And then I think the initial decay in the bigger system has to do with the fact that because we're considering some local dynamics, the bigger system doesn't know that it's the bigger system until things somehow reach the edge of the system. But then after that point, it actually something changes. Okay. So for a subsystem bigger than half, essentially our intuition for thermalization was completely wrong. Okay, so we can also consider the integrable case of this pinching, where we turn off the longitudinal coupling. And in this case, we see a very strikingly different behavior of this quantum Fisher information. So again, this is the analog of the same plot where I fix the subsystem size to be 1 and increase the size of the full system from 9 to 12 in this case. And I find that, unlike the previous plot where I found monotonic decay and then the late time values were exponentially decaying with the full system size, here I find that they are not decaying at all with the full system size. Okay, so in the integrable case, even the smaller subsystem is not equilibrating. Yeah, this is striking because in the case of the entanglement entropy, if I just looked at the entanglement growth in both the chaotic and integrable spin chains, I would see more fluctuations in the integrable case, but the average late time value would be the same as the chaotic case. So somehow the entanglement entropy only captures the behavior of the eigenvalues of the density matrix, and looking at the structure of the eigenvectors as well as we do in this quantity is able to probe the difference very sharply between the integrable and chaotic cases. Yep.
How do you explain this dip down and goes back up?
In the integrable case, I don't understand it very well. I think, yeah, so I want to understand it better using this quasi-particle model, but applying that is slightly complicated. It's not too complicated, but it's slightly complicated, and I haven't understood it fully yet. But yeah, but it's essentially, one thing I should say is like if I had made the plot for the case of a chaotic system for bigger than half of the system, like if I took 7 sides and then increased the full system size from 9 to 12 or something, then I would see a plot very similar to this one. So somehow in the integrable case, there isn't a difference between the smaller subsystem and the bigger subsystem. And both are not equilibrating.
Yeah, I don't know if you're gonna get to this. I was just curious, like, does the position of that diff relate to this? I assume like it's like how quick information needs to propagate to like the domain walls or something. Because it seems to shift with the size of the system.
Yeah.
Yeah.
Yeah, it seems like it might be related to something like when the information circles around and comes back.
Yeah.
Yeah, but I don't fully understand it in detail. Okay. Okay. So So because we're interested in black holes, let's focus mostly on the late time state in the chaotic case. And let's try to understand the scaling that we found for the saturation value by using some simple model for the late time state. So as I already mentioned in these calculations of the entanglement entropy, a very natural model to use for the late time state was a uniformly drawn random pure state on the combined system. But in this case, it turns out that because this quantity was very complicated, it's very hard to actually use a random pure state as a model and do the calculation analytically. That requires doing a very complicated replica trick, which we didn't want to do. But we're not particularly attached to a uniformly random pure state. We just want to come up with some random model where it's easy to do calculations, which we expect roughly matches the structure of our late time state. So what we'll do instead is, I think I mentioned that there's an explicit formula in terms of the Schmidt decomposition, which is not too complicated for the Fisher information. So we will assume that the Schmidt decomposition has this form, where we assume that all the Schmidt eigenvalues are just equal to 1 over square root of dA, where A is the smaller subsystem. And then take an arbitrary basis for the reduced, take an arbitrary basis for the Schmidt vectors in A. And then take a random set of orthogonal Schmidt vectors in A bar, and the set has size dA. Okay, so it's like you pick some arbitrary vectors, some dA arbitrary vectors phi I in A bar, and then act on them with some random unitary. Okay, this is not exactly what the structure of a random pure state is, because there's also some kind of small amount of level repulsion between these different eigenvalues in that case, so they're not exactly degenerate. But it turns out that you can also include effects like that, and the answer doesn't change too much. Yeah.
So I was saying A bar is A, the system that the subset, and A bar is the exterior to that subset.
Yeah, yeah. So in particular, in this model, I'm assuming that A is the smaller subsystem and A bar is the bigger subsystem. Yeah. Okay. So here I'm assuming not only that the states are highly entangled because all the Schmidt eigenvalues are equal to 1 over dA, or all the PIs are equal to 1 over dA, but also that it's highly entangled in a very random basis. Yeah.
Shreya, how exactly do you, the Fisher information involves a time derivative, but you're giving me a model that's like a state at an instant of time.
Yeah.
How does that get, how do you calculate with this?
Yeah, so as you said, this model knows nothing about the actual time evolution of the state, but I can always, I want to consider something like the instantaneous time evolution of the state. So the formula for the Fisher information involves a commutator of H with the state at whatever time you have. So I'm just going to forget that the state actually came from time evolution by H.
Yeah, that's fine, but what's H in this? I mean, H is.
I'm taking H to, for instance, be the same as in the spin chain model.
Okay, so you have some fixed H on a spin chain.
Yeah.
And you give me one of these like random Schmidt states.
Yeah.
And you want to compute the commutators of H.
Yeah, yeah. And somehow I'm assuming that clearly if I had some initial state which was very constrained by energy conservation, like an actual eigenstate, then this would be a terrible model. Because I should find that the value is 0 and I'll find something non-zero from this. But somehow, if I take initial random product states, they have a very high energy variance, so they're not supposed to be very sensitive to the effects of energy conservation. So this is somehow, yeah, so right. So we were not sure if this would work, but it turns out that despite not knowing that the state was obtained from evolution by H, it works extremely well to explain the scale. So yeah, so the fact that the state came from H is actually not important for explaining that scaling. Okay, so what we find is we plug into this model for the state into the expression for the Fisher information, we calculate the random averages, and we find some expressions which involve the dimension of A, the dimension of the full system, and different traces of the Hamiltonian. Okay, and we can divide the Hamiltonian into the part in A and the part in A bar and some interaction term. And we get expressions like this, which in the limit of large dimensions exactly match the scaling that we found in the spin chain, where you find dA squared over D times the area of the boundary of the subsystem for A less than half of the system. And then you find this other scaling where you find that it's proportional to the size of the subsystem A and independent of the size of the full system for this case.
Sure, maybe
Yeah.
now I can return to my previous question and
Yeah.
ask, what assumptions are being made about HA and about the interaction term that give you this scaling?
I'm assuming that it's essentially like in the spin chain model that I was considering. So you have a sum of traceless local terms. which are supported on some order one number of sites.
Mhm.
So HA consists of NA such terms approximately, and HA bar consists of NA bar such terms, and H int is some order one number of terms.
Thanks.
Can you go back to the previous slide for a
Yeah.
second? I'm a little bit confused about how a Haar random state and the time evolution of a Haar random state is possibly well modeled by what
Okay,
you just discussed.
okay.
The Hamiltonian you just described sounds nothing like something that would give rise to a Haar random unitary.
At late enough times, actually, so as I mentioned, the value of the entanglement entropy of the state at late times is exactly the page value.
Okay.
So that suggests that, once you have explored the whole system, like at times that are bigger than the size of the whole system.
Yeah.
From the perspective of many quantities, there is no difference between a Haar random unitary and, in particular, from the perspective of the entanglement entropy, there's no difference between Haar random state and the actual state.
Okay.
And then we want to check whether or not that's also true of this quantity. It would not be true of very fine-grained quantities, probably.
Yes, of course.
Yeah. Mhm.
And where are you using the Haar measure here?
I'm not well, I'm assuming that the measure on these unitaries is a Haar measure on of unitaries on A bar.
Mhm.
But I'm not actually using the Haar measure of states on the whole system, because that would give me a much more complicated model where I could, in principle, have some correlations between the eigenvalues here, the eigenvalues here, the eigenvectors in A
Yeah.
and the eigenvectors in A bar.
I'm just confused as to what Haar randomness actually buys you in this frequently used model.
In the original.
Yeah, like what do you actually gain by using a Haar random state? If you're not using typicality and you're not using the Haar measure,
Yeah,
what does it gain you?
An analytic calculation, maybe?
But for that, you'd have to do the Haar measure somewhere.
Yeah,
I'm
but she's
not
using
seeing-
it on the second.
Yeah.
She's using the Haar measure on A bar.
on the
Okay,
A bar.
oh,
Yeah,
I see
yeah.
on A bar, I
She's-
see,
she's
I
gonna
see,
do the
okay.
intervals
Yeah.
over that, yeah.
Okay,
Right.
okay, yeah.
And that is very important because if I assume that they're entangled, if the Schmidt vectors are very simple, like if I just have some string here and the corresponding string in A bar or something like that, then I get a very different scaling and that the answer looks more like the quasi-particle model.
I see, yeah.
But the entanglement entropy doesn't know anything about this structure, so, yeah. Mhm. But yeah, I'm making an assumption here that the actual structure of the eigenvalues is not very important. The fact that in a Haar random state, you actually get some non-trivial distribution of these. And even if I include that non-trivial distribution by replacing this model with a slightly more complicated one, I find that the corrections from that are exponentially suppressed.
Good, okay.
Okay, so good. So this is the result that I get. It matches the scaling from the spin chain. You can also check in a little more detail. So in this plot, I'm plotting as a function of NA divided by the number of qubits in the whole system. And I'm plotting the value of the Fisher information divided by the size of the system. And the circles here are values that I obtained from actual time averages after the saturation time. So in plots that I showed you at some point, these became constant and then averaging over some range of times in that for different subsystem sizes and full system sizes. Okay, so I get some behavior like this. Then I can compare this to what I get from my toy model. And I can also introduce some further finite size corrections to these leading terms. And then I get the plot in the stars. So it's not quite the same value, but it's quite similar in qualitative behavior. Okay, and if I now look at the n going to infinity limit of the toy model, then I get this abrupt transition at the halfway point, where before the halfway point, the value of the Fisher information is negligible, and then it suddenly improves to an extensive value at the halfway point, and then it continues to improve as I further enlarge my system. Okay. And yeah. Okay, so that is one of the main results. So yeah.
So the conclusion is the system is too small, you can't tell what time has passed, and if it's a big.
Yeah, at late times,
At late
your
times,
ability, yeah.
It needs to be a sufficiently large for you to tell.
Yeah.
Okay,
But suddenly when it becomes more than half, you can tell very well.
okay.
Okay, so let's just sort of understand these results now in the context of evaporating black holes. So recall that this was our setup, that we were given rho r at some time t plus delta t, which is close to something t. But we're fixing the sizes of B and R, so we're not considering sort of transfer degree of freedom from B to R. And again, if we use either the late time state of the chaotic spin chain or a random toy model state as a model for this state, then the result in both cases is the same. And what we learned from this is that time estimate is very unreliable before the page time, so it has a huge variance. But suddenly, after the page time, the variance suddenly improves, and then it continues to improve until the end of the evaporation process. Okay, so for those in the audience who have worked on the black hole information problem, this might remind us of something else called the Hayden-Preskel experiment, where okay, so let's recall sort of what we said about the entanglement entropy at the beginning of the talk. That the entanglement entropy of the radiation stops looking thermal after the page time. And in particular, this suggests in some vague sense that the radiation must contain some information after the page time. But this was made very precise by Hayden and Preskel by considering an operational task, where they consider the following setup, where you imagine throwing some diary in some state rho d into the black hole. And then subsequently, the black hole evolves under some evolution, which we assume is chaotic and unitary. And then at late times, we divide the system into two parts, the remaining black hole and the radiation. And we ask how well we can recover the state rho d by processing the state of the radiation. Okay? So even in principle, if we used optimal measurements or optimal operations, how well can we recover? And they found that the recovery is very poor before the page time, and then it's almost perfect after the page time. So it's very similar in structure to this result that we just found. And we can ask if there is some.
So in this
yeah.
context, page time is the page time for the entire black hole?
Yeah,
or is it when half the diary mass is evaporated?
Oh, so I'm assuming the number of degrees of freedom in the diary is negligible.
Negligible, okay,
Yeah.
right. So you don't need to wait just the time for that amount of information to escape. You have to wait for the full page time of the entire black hole.
Yeah.
Okay.
If you had considered a diary size scales of the black hole, then the time would be like proportional to would be page time plus something proportional to the number of degrees of freedom.
Number of degrees. Okay, fine.
Right. So this result has a similar flavor to what we just found. And we can ask, is there a more detailed comparison between these things? Are they coming from the same thing and so on? So let's try to understand what happened, how we formulate the Hayden-Preskel protocol in more detail. So in that setup, we imagine that we're encoding, we're going to phrase this in terms of error correction. We imagine encoding the state of the diary, which is a state on 1 qubit into n qubits in the following way, where we have some initial state of the black hole, and we put whatever state of the diary we have, then unitarily evolve them together under some highly scrambling chaotic unitary. And at late times, we trace out the state of the black hole, so we're left with the state of radiation. And so this is some quantum channel from the Hilbert space of the diary to the Hilbert space of the radiation. We can ask about, if I consider two initial states, psi and phi, under this channel, then they would initially have some amount of distinguishability. We can ask if they remain equally distinguishable after the channel. Okay, so if they do, then we would say that the information recovery is perfect. And then if they become less distinguishable after the channel than before, then we say that the information recovery is imperfect. If they become completely indistinguishable, we say that you can't recover the information at all. Okay, so we can use a particular measure of the distinguishability called the fidelity, which is equal to 1 if the states are completely indistinguishable, and equal to 0 if the states can be distinguished well. Okay. And it turns out that in this Hayden-Preskel setup, if you consider two arbitrary initial states, then this fidelity after you activate the channel is 1 if dr is less than dB. So that's before the page time. And it's just equal to the initial value if dB is less than dr. So the distinguishability becomes perfect immediately after the page time. Okay. So now we can ask whether we can introduce some analog of this in our setup. So what we want to do is essentially distinguish the state psi of t from the state obtained from infinitesimal further time evolution, which can be Taylor expanded like this. So this is essentially the task of distinguishing two states like this, where you can imagine encoding some 0 state into just psi 0, and then act on it with the Hamiltonian up to time t. And then you want to distinguish that from roughly the state where you further act by 1 step with h in that state. And of course, you should actually orthogonalize these two states, but roughly this is what you want to do. And we can see that this has a somewhat similar structure to what we were doing in the Hayden-Preskel case, but it's also different because we're not somehow using the full power of the random unitary in this case to scramble the information. We're just using the same unitary of both 0 and 1, and then acting with H after that. Okay, so, yeah, and then again, what we're trying to do is sort of analogous to trying to distinguish these two states after tracing out some subsystem B. Okay, and we can calculate this more directly. So we can see if we act with this channel where we trace out B, then the fidelity between the 0 and 1 states that we defined is just equal to 1 before the page time. So they're completely indistinguishable before the page time. And then after the page time, we see this value of NB over N. So that means that from 1, it suddenly drops to 1/2 at the page time. So there is a sudden improvement in the distinguishability, but it's still not perfect. And then it continues to decay further until the end of the evaporation process and eventually becomes 0. Okay, so it's similar in structure, but also different from the Halley Westwood protocol. Okay, good. So, okay, so since I think I only have 5 more minutes, I'm going to maybe skip some of the things I was going to say about the structure of the time-of state. Yeah, so roughly this is providing more intuition for why the values behave in the way that I said. So for a smaller subsystem, it's the fact that the value is small, as I already mentioned, is intuitive from the fact that the state is equilibrating to the to the maximally mixed state. But what this quantity is probing is actually something a little bit different because it's probing the velocity at which the state is changing, which is not probed by just looking at the absolute distance from the maximally mixed state. And then, yeah, there is some natural physical interpretation of the large value for more than half of the system in terms of how much the Schmidt basis of the state in the larger subsystem is changing as a function of time. So it's somehow, because we have some Schmidt basis of dA vectors in a dA bi-dimensional Hilbert space, it actually has a lot of room to move around in the whole Hilbert space after the page time. And so it really, the fact that the value is large is telling us roughly that these eigenvectors are exploring the whole Hilbert space and not equilibrating to anything. Yeah, this, which is more detailed models for the time evolution and the integrable and chaotic cases. But I want to talk about the case where now we restrict to the case of simple measurements because that has some interesting interaction with some things that people here are looking at. So, so far we said that we already discussed that if we have the state e to the minus beta h, which is the actual thermal state, then the quantum Fisher information would be 0 for any subsystem. And so there is an infinite uncertainty in estimating time for this state. In contrast, if we consider the state psi of t and the NR obtained from the unitary chaotic evolution, sorry, this is not right. So if we consider the state, then if we consider the state before the page time, then the value of the quantum Fisher information is exponentially small in n. So it's essentially almost the same as the 0, and it's not very different between the thermal state and the actual state. But after the page time, the quantum Fisher information of the radiation becomes of order n, which is very different from this value of 0 in the thermal state. Okay, so this is telling us that by using optimal measurements on the radiation, this quantity is able to very sharply distinguish between the thermal state and the state after the page time. But we can now consider what happens if we consider simple measurements on the radiation instead of considering optimal measurements. Okay, so in particular, one thing we can do is just fix the measurement basis to be the computational basis and study the classical Fisher information associated with that. Okay, and intuitively, we expect that we would see some kind of information loss from the perspective of simple measurements, even if we have a big subsystem. So this was these were some ideas which were developed by Netter and Aaron Wall. And in this setup, the analog of information loss from the perspective of simple measurements, we might imagine would be that the corresponding classical Fisher information associated with simple measurements is close to 0, even if you consider a bigger than half subsystem. Okay. So the first thing we can do is just consider the full system and consider simple measurements on that. Okay, and the classical Fisher information associated with such measurements. And then we find that this intuition based on information loss does not turn out to be correct. So we find, in the case of the time evolution in the chaotic system, we find these solid curves. So I'm plotting this for the full system, but changing the size of the full system from 8 to 11. And I find that the late time value is smaller than the initial value, but it's still proportional to the size of the whole system. Okay. So in particular, and then the dashed lines are the same calculation if I have some random state of the whole system. Okay, yeah, so I find that in this case, the value of that I would predict for the classical Fisher information on the whole system is proportional to volume, which is very different from the value of 0 in the actual thermal state. Okay, but then I can imagine restricting to some subsystem. So I have a subsystem which is bigger than half of the system, but still not quite the full system. This is like the state of the radiation after the page time, but not quite at the end of the evaporation process. And in this case, I find this kind of behavior where it's decaying. So there's a path that's proportional to the size of the whole system, but then it's decaying exponentially with the size of the complementary system. Okay, so in particular, in the black hole case, this means that there's an exponential decay with the number of qubits in B. So if we're at, yeah, and you can see this in this plot where I'm fixing the size of the full system to be 7, and then increasing the, sorry, fixing the size of the subsystem to be 7 and increasing the size of the full system from 8 to 11, and I'm seeing an exponential decay with the size of the full system. This is in contrast to the quantum Fisher information in the same setup, where it looks like it's decaying a little bit with the system size, but actually these numerical values are very close to each other. Okay, so that quantity does not scale with the size of the full system, but here it really does.
And this big dip is not there in the left.
Yeah, yeah, exactly. So it's also more kind of like classical.
Looks more random.
Yeah.
Yeah.
Right. So
What is the big dip? What's going on?
You haven't heard that yet.
yeah, I actually skipped that part, but maybe I'll come back to it after finishing this part of it.
Mystery dip.
Yeah. Okay. So yeah, so this is telling us that the computational basis classical Fisher information does distinguish the state on the radiation from each of the minus. Sorry, it does distinguish it only in the case where we're close to the end of the evaporation process, when this thing is actually large. So that's when the number of qubits in the black hole is proportional to log n. Okay, so it's really at very late times.
Sarah, is it classical Fisher information just with a classical Hamiltonian instead of a quantum Hamiltonian? Sorry.
No, so I'm using the same Hamiltonian and I get the same time evolved state. But as I mentioned right in the beginning when I was introducing these quantities, you can choose to measure either in some fixed basis.
Yeah.
And look at the classical Fisher information associated with that, or you can measure the optimal basis, which gives you the quantum Fisher information.
So there's a difference in basis.
Yeah, so here I'm choosing to just measure in the 0-1 basis of the Pauli Z operator, which is the simplest possible thing I can measure. Okay. Yeah, so right. So this is telling me that if I have times which are after the page time, but still not close to the end of the evaporation process, this is not letting me distinguish it. Distinguish them using yeah. Can I have a couple more minutes or?
I think maybe it's better to wrap up and then we can do
Okay.
some questions.
Okay, sure. So this is what I think is like an explicit operational procedure for distinguishing the two states based on the difference in the value of the classical Fisher informations. I also wanted to mention that the fact that things become distinguishable using simple operations only at the end of the evaporation or close to the end of the evaporation process is consistent with the expectation that you would have based on the swap test, which is another simple thing that you could try to do to distinguish the two states. Again, it only works at the same time scale, but from a completely different calculation, completely different perspective. So this was mentioned in the paper of Netta and Evita. Okay, yeah, I'm also going to skip this, but basically by looking at the trace distance, you also recover the same. You can look at the classical trace distance between these two classical probability distributions in the computation basis, and you recover exactly the same kind of intuitions about when you can distinguish them and when you cannot. Okay, so yeah, so basically in this talk, we discussed this distinction between thermal density matrix and actual state at late times, which is that the former does not evolve with time, while the latter necessarily evolves with time by using this operational task of time estimation. And yeah, in particular, we found there was a sudden transition of the page time. Maybe I'll leave you with a question, which is, here I did sort of the analog of pages calculation, which is predicting how this quantity actually behaves in some microscopic description of the theory. But if we could calculate this using semi-classical gravity, would we see some analog of information loss like we do in Hawking's calculation, where maybe even for bigger than half of the system, we would find that the Fisher information is still very small. Yes, that might be an interesting set of things to explore in the future, whether that's true, and then if so, then how is the information loss resolved in this case? Yeah. Okay.
In the example of the spin change, was the power law decay, was the power related to hydrodynamics or was there some other?
The power law decay, I think. That's a good question. I expect it might not be related to hydrodynamics because I'm considering an initial ensemble which doesn't care about energy conservation too much. Yeah, so I think that there's a lot to explore in the details of the time evolution, which we haven't understood in enough detail. Yeah, but like another question related to that is whether if you had considered an initial state which cares a lot about energy conservation because it has some order one variance, then is the time evolution very different in that case?
So you give a very nice interpretation as in evaporated black holes. I'm actually trying to like interpret it in an alternative way in terms of a non-evaporating black hole. So like the spin chain setup you're thinking about is basically a global quench, right? And then a generic global quench can be modeled using a collapsing black hole.
Yeah.
Like in above. So probably like this very deep down is a collapsing collapsing star phase, where the black hole is not formed yet, and this corresponds to the stage where the horizons are here. I see.
Yeah.
So it's
Yeah. So from that perspective, it would be interesting to see whether, like, again, if you could do a steady-state gravity calculation, if you would see this increase at intermediate times, or if you would just see it keeps decaying even further.
and I think that's actually pretty like related to Matthew's question, because like if you use like perfect fluid to like to model this collapsing star, probably that has a hydrodynamics like interpretation as commented by Matthew. I'm not sure.
You mean in the boundary theory or in the bulk theory?
I mean in the bulk theory.
Okay. Yeah, that's a good point. Right? It would be something like the decay of 2-point functions, like the same kind of physics that governs the decay of 2-point functions.
So yeah.
But I guess some of those are governed by energy conservation and other ones are not, so I'm not sure.
Yeah.
Sure.
Maybe, let's have one final question if it's really pressing, and then let's save other questions for lunch.
I was just curious what the boundary condition you picked for the system was.
Oh, it's periodic boundary condition.
Periodic.
Great. Lunch it is. That's like your-